in the homework and the quiz, and then we'll start with the practical exercises. So I think one of the questions that most of you had trouble was relating the lensing potential and the gravitational potential. That's not the question there, but it was to relate psi to, let me pull that up. Was that homework 2? Yeah. Yes. Okay, so the starting point will be to start from the Gauss's law for Newtonian gravity. That would be to say, so I'm writing it the other way around. So I have 4 pi g three-dimensional density. So let me call that chi1, chi2 and r3. So this is equal to the del square of the Newtonian gravitational potential, and I will write this explicitly as this. So I just written the Gauss's law with all the parameters, the dependence explicit, and I've expanded the Laplacian. Now to get to kappa, or the two-dimensional mass density, I will start by integrating over all of R3. So say 4 pi g integral 0 to infinity of chi1, chi2, r3, d r3, and that's same as
Arun?
Yes.
May I ask something?
Yeah.
Why are the limits between 0 and infinity?
Yes, it should be actually till.
What I think is that R3 is not a radial coordinate; it's just a Cartesian coordinate.
Yes,
so it should be between minus infinite and infinite.
Okay, so I am assuming that the source is at infinity, but if not, we can write this as ds. So you're right, it doesn't have to go. So the lensing happens by all the mass between us at 0 and the source at ds. So we are at the coordinates where r3 is 0. So we are 0 distance from our own line of sight, and the source is at a distance ds. Yeah, this is probably better. So chi1, chi2, r3, they are all perpendicular directions. So something like chi1, chi2 and r3 is into the bowl. So because they are orthogonal, I can bring this differential out and take the integration in. I can write this as del square by del chi1 square integral dr3 from 0 to ds, and similarly for chi2. So chi1 and chi2 are not angular distance, but they are the physical distance or the physical coordinates. And this is the crucial part. So I cannot do the same that I did to chi1 and chi2 because now these are same coordinates. Instead, I will write this as dr3 del by del r3 of some other quantity, which is the which is the partial derivative of phi itself. So now I have dr3 and a d by dr3. So this will remain the same. So this is like saying if you integrate a derivative, you should get back the same function. But then this is a definite integral, you have the limits. So this would mean you get d phi by dr3 evaluated at ds minus so this is similar to saying f of dx d by dx of some f of x is f of x. Except that, so this f of x is equal to this del phi by del r3 itself, and I have the same one, except that this is in multi-dimension, so I have a partial derivative, but this is same as this, but this is an indefinite integral, but since I have the limits, I have to subtract these two terms evaluated at the boundaries. And then you use the assumption that phi dies down sufficiently fast away from the lens itself, which means the potential due to the lens at the position of the source is very negligible, and the position and the potential due to the lens at the location of the observer are negligible. So phi r3 equal to ds. So this is due to the lens. So I am saying that the potential has died down by the time we go to r3 equal to ds or to 0. So that the derivative is also 0. So both of these terms are individually zeros, so I can just cancel them. And I realize that this is two-dimensional Laplacian, but in chi variables. So I have to write this in terms of theta variables to relate it back to the equation for kappa. So this is Laplacian with theta as the variable, but we also know chi is delta dl times theta. So I can remove the dl outside and write this as and on the left hand side this is the surface mass density, so that is 4 pi g sigma of chi 1 and chi 2. And also remember that kappa by definition is sigma by sigma critical, and sigma critical is c square by 4 pi g d ds dl dls. So now I can replace this sigma, the surface mass density, by sigma critical times kappa, and I can write the expression for sigma critical. So the 4 pi g cancels here, and I can take the c square and the distance terms on the other sides. So I get kappa equal to 1 divided by dl squared, and then the c square comes down. So I brought these terms on this side, and I have the Laplacian in theta times phi. Is this clear so far? And now I use the fact that kappa is also given by half Laplacian in theta times the lensing potential psi, which is equal to this quantity 1 by c squared dls dl ds. Or I can take this 2 to the other side and subtract, and I can write the Laplacian in theta times psi minus dls dl ds 2 by c squared So I have just taken this 2 on the other side and then subtracted. So maybe at this level you might be tempted to say, okay, there is del Laplacian square on the other side, therefore half of psi should be this factor times the integral of potential. That's essentially the correct answer, but it's correct for very subtle reasons. You should write like this first, and then the argument is to say this has the boundary conditions of 0 at sufficiently far away from the lens and the source. That is, at infinity, this has boundary conditions of 0, and the uniqueness theorem for Laplacian of some function equals 0 says that if it is 0 at all boundaries, then this is identically 0. So it's a mathematical statement, it's a theorem that says that this function is identically 0, and that would say that psi is equal to this. But even if you did not make this argument and you just jumped from here to saying psi is equal to this quantity, I am going to give you marks, but the argument is very subtle. So let me write down the argument. Can I erase this part? I will erase this. So this is a statement saying that if it is boundary at all edges, if it is 0 at all of its boundary at the edges, then it is 0 everywhere, because the theorem says that it cannot have a local minima or a local maxima, and if it is not 0 somewhere, then it would mean that it has a local minima or maxima, and that's a contradiction. So a way of visualizing this is to go to one dimension and say, what is the solution corresponding to second derivative being 0? That is, for this is not clear. So for what functions of f is del square by del x square of f is 0? Okay, x, and is that the only function? Constant, yeah. Constant times x. Even more general. Yeah, all linear functions. So it's a second derivative. So that means there should be two unknown constants. So the solution for this would be f of x is sum mx plus c for any values of m and any values of c. That is, so the solution of this equation is the set of all straight lines, and straight lines do not have any local minima or maxima. So the solutions to this equations do not admit any maxima and minima, and if it has to be 0 on two ends, then it has to, if it increases, if it has to decrease, which means there would be a maxima, or if it decreases here, then it should have a minima and then increase again. Since the solutions don't admit a maxima or minima, it has to be flat 0. So that's the argument. So even if you don't give this argument, it's fine as long as you make this equation, you get this equation. Yes. Had a question?
What does the integral that
ends up
on the expression mean? Or it's just like an integral you should do in the case you have the potential?
Yeah, so if there are a bunch of particles, so I haven't specified what the potential is. All this says is, if you give me some gravitational potential, or if you give me some system of particles or a collection of masses or lengths, find the gravitational potential corresponding to that mass distribution, integrated all the way from 0 to the source. So this goes from 0 to ds. So if you specify a gravitational potential corresponding to a length located at some dl, then I can tell you what is the lensing potential for the particular source and the particular length. So any questions on this? I think most of you got the answer for the isothermal non-singular isothermal sphere correct, except that some of you had also differentiated with respect to theta c. That was incorrect. Theta c was just a constant and not a coordinate, but otherwise I think everybody got the answer correctly. But do you want me to discuss that, or can we skip that? And if there is no particular request for that, so I will post the solutions, but if there is no particular request for discussing that, then we can skip it.